Hi again, everyone. Today we're going to look at a line integral. Okay, now a line integral is just a generalization of the regular integral that you learn at school, and in particular the line integral is useful for computing work. For example, when a non-constant force is applied to an object that moves not necessarily in a straight line. Okay, now up here, this is the line integral that we are asked to evaluate. Notice that we've got some differentials here, and this curly C is the upper half of the ellipse parameterized by this vector function, C, and in particular, our curve curly C being the upper half is just from t equals 0 to t equals pi. Okay, so our curve curly C is this particular half of an ellipse. Now, notice that the direction in which the top half of the curve of that ellipse is traced out is the anti-clockwise direction. Okay? Okay, so how do we evaluate this particular line integral? Well, notice that we're given the parameterization or the description for the curve. Now, it's important to recognise also that this is one particular description for this curve. There are other descriptions available, but this is a nice simple description, so let's use that. We're also given it, so it would make sense to use it. Okay. Along our curve curly C, we have the following. All right, x is equal to 3 cos t, and y is equal to 2 sin t. Okay, so what we do now is calculate the differentials here, and what we're going to do is back substitute into this original line integral. Okay. Okay, so what we do now is take these four expressions and back substitute into the line integral. Now, what do we do here with the limits of integration? Well, we just replace them with the lower limit of t equals 0 and an upper limit of t equals pi. Through this substitution, we reduce this line integral back to a regular integral that we know how to evaluate. Okay, so we're going to be integrating from 0 to pi. We're going to replace 9x with 9 times 3 cos t, which is 27 cos t, multiplied by dy, which is 2 cos t to t. Okay, and then minus 9 times y, which is minus 9 times 2 sin t. And substitute for that dx, which is going to be minus 3 sine t dt. Okay, so now what we do is we take the common dt's and place them out on the right-hand side, and if you look closely, we should get the following after cleaning up a bit. Okay, so now we've reduced our line integral I down to something that we can easily evaluate. Now notice that cos squared plus sine squared equals 1, so this is just 54. Okay, 54 times this simple integral here, which of course is just 54 pi. Okay, so we have our answer. Notice our answer is just a real number here. Okay, so what does this answer mean? Well, if we were considering, say, a vector valued function, say minus 9y comma 9x, and we were moving a particle around this curve in an anti-clockwise direction, then this number here would represent the work done by the force in moving the particle around the curve. Okay, there are lots of other applications. One thing to remember with line integrals is that direction is important. So, for example, if we were going the other way, we would actually get a negative here. So direction is important, and that comes back to the parameterization.